concerning this afternoon, Glenn Stevens will be speaking at 2:30 on the construction of the eigencurve. Now, people working in other groups may want to work on the project. So some of the other people could stay out in the main hall outside to work on your project. The buses will be coming to take you back to the hotel at a time that might be 3:30 or 4. We need to figure that out, and we'll make another announcement about it. But basically, we don't have the rooms in the hotel that you normally use in the evening. So if you want to work, it will be out there or here in the afternoon. Right? And all right, so 20 plus 50, 10 after. 10 after. Okay. This is your last one, right? So Kartik's last talk now.
Yeah. Okay. Can you hear me back there? Yes? I don't think so. Can people hear me back there? Yes. Okay. Yeah. Right. So I'm going to continue talking about the stuff I was last time. But before that, I want to just make a few general comments about questions that came up. So these are maybe of a more philosophical nature. But so the first comment is I was talking about the Tate conjecture and applications to periods. But the Tate conjecture really usually predicts something in the Chow group tensor QL. Okay, and so the question is, how do you go from here to periods? The point is that you can, if you find a cycle in the Chow group tensor QL, you can approximate it by something in the Chow group tensor Q. So and if you use multiplicity 1 in addition to that, then that would suffice to tell you that there should be some kind of period relation. But the interesting thing is that in any case, the Tate conjecture or the Hodge conjecture are not expected to be integrally true. So you can't replace the QL with the ZL, for example. Okay? So the Hodge and the Tate conjecture are not expected to be integral versions. Are not expected to be true. So you might wonder, why do integral period relations exist? Sorry? That's right. They're false at Eisenstein primes, right? That in our case. So it's an interesting question. I don't know if anybody has thought about this, but I just want to throw it out. Can you kind of bound the denominators in the Hodge or Tate conjecture in terms of Eisenstein primes or anything like that? Okay? So I'm just going to throw that out as a question. Can we bound denominators? Let's say the Tate conjecture. Okay, that's just a question. I don't know anything about that. So, all right. So the second point I want to make is last time I talked about theta lifts, theta correspondence. And there are very interesting, many interesting questions that come up. The first question is usually, I wrote down something. For all you know, what I wrote down was 0, right? So when is it not 0? So non-vanishing of theta ellipsis. It turns out this can be a very subtle question. For example, it could depend on both local conditions, and you'll see one of these in a bit, having to do with epsilon factors, for example, and there could be global conditions, and these typically involve an L value. And we all know if the L value turns out to be the value of the center, it could vanish, and that could give you obstructions to vanishing, to non-vanishing for theta lifts. Okay, all right, and right, of course, and in the case I'm looking at, or in the case I'm looking at, we're interested not just in non-vanishing, but we're interested in maybe algebraicity of theta lifts, and / integrality of theta lifts. And these turn out to be related to questions in Iwasawa theory. And the most interesting thing is sometimes you want to prove that a theta lift is a p unit. That in fact what you get is a p unit. And this turns out to be typically the hardest part of the whole game. In Iwasawa theory, it's a very difficult question in general, given a family of objects or numbers, to show that at least one of them is a p unit. This turns out to be a very vexing question. So these are some general points that I want to make. And now I'm going to come back to what I was talking about last time. So recall what we'd like to do is to understand this conjecture on periods, and I'm going to go to the totally real case. And there are two approaches in this case to the algebraic results, at least. So the first is the approach due to Harris, and this uses unitary groups. And the second is some ongoing work with Ichino that uses quaternionic unitary groups. Now, I wanted to say more about the first approach, but for lack of time, I'm mainly going to talk about the second. But I just want to say a few words quickly about Harris's work. Okay? So the basic idea is that if you have two quaternion algebras, say B and B prime, you want to understand how to transfer automorphic forms from B cross to B prime cross. Okay? And Harris's idea is you pick should I call this E? Let me call this E. You pick E over F, a CM extension, so a CM field, such that E embeds in both B and B prime. Now, if E embeds in B, for example, then you can write B as the direct sum of E plus an orthogonal complement for the norm form. And you can think of B, so think of B as an E vector space. In fact, let me think of it as a right E vector space. Okay. Now, remember that on B there was the usual form, which was just xy equals xyi plus yxi, where I is the main involution. So that's a symmetric form. It's an F linear form. Now it turns out that B is an E vector space, and you can make B into a unitary space. In the following way, you define the following form. We call it bracket xy, and this is just the following. So you take x, I, y, and project it down. So maybe yeah. So maybe I should have taken something like that. Okay, and project it down to the first coordinate over here. So let me write this projection map, I'll call it PR, and take this projection map. And it turns out that you can check that this form, so this is an E Hermitian form. Yes. Yes, okay, so then so I should maybe take, so that's what I want, right? Yeah. That's right, but this is also E plus J E, because the relation between, because that's an orthogonal complement, right? So alpha J equals J alpha bar for alpha in E. Right. So the point is now you have a two-dimensional Hermitian space, right? And you can think of the unitary group of B, right, UEB, or in fact more generally the general unitary group. Okay, and now it's not hard to show that in fact, so this is going to be contained inside the orthogonal group because the trace of this form equals the usual form. And in fact, what you can check is that, so remember the orthogonal group was something like B cross cross B cross mod F cross. This turns out to be B cross cross K cross mod F cross. Okay. Sorry? Oh, I need to lift that. Yeah, okay. Okay? Right. So in the orthogonal group, number these as we go along. Yeah. I know, I should. All right, I'll rotate it. Okay. Yeah, it's just that I've been doing this route. So, is this better? Oh, yeah, I could try zooming out also. Okay. Okay, I'll write like this. Is this going to fit? Okay. So you see so earlier we were looking at the orthogonal group, and then forms in the orthogonal group consisted of pairs of forms pi1, pi2 whose central characters agreed, right? Or whose product of the central characters is trivial rather. But now the unitary group is of the form B cross cross K cross mod F cross. So a form on the unitary group. Oh, I have that paper already. Oh, K is E. Very good, thank you. So I'm used to it. Yeah, K is E. So a form on GUEB is a pair pi comma chi, where pi is a form on B cross, and chi is a form on K cross on E cross. But of course, the form on E cross is just a Hecke character of E cross. But then you're going mod F cross, so there's a condition on pi and chi, namely that the condition is that if I take the central character of pi times the central character of chi, this should be 1. Okay. So now you can do the following. You can take these two. You can take B and B prime. Think of them both as unitary spaces, and if you remember what I did in the last class, you can define a theta lift from UEB to UEB prime. Okay. The point is they're both unitary spaces. So one thing that you have to do is the way I've written it. They're both Hermitian spaces. You have to convert one of them into a skew Hermitian space, but it's very easy to do that. You just multiply the form by an element of trace 0, and that makes it skew Hermitian. Okay. So then you can make the theta lift because you can tensor the skew Hermitian space and the Hermitian space, and think of that as an F space. Okay. And that has a symplectic form, and so you get a dual reductive there, as in the last class. And essentially what Harris does is he studies the arithmetic of this theta lift. Okay. This turns out to be quite subtle for many reasons. The first is that this theta lift could vanish. Okay. There are local, as I said, there are local and global conditions involving epsilon factors and an L value. So the epsilon and the L value in question is in fact the central value L half pi chi. This is the Rankin-Selberg L function. So there are a fair number of subtleties that go into this. And the third subtlety is the following. You remember that when we were looking at so just to recall, in the old case where we looked at the lift from GL2 to B cross cross B cross, mod F cross, this was the Shimizu lift. To understand this lift, we in fact study the lift in the opposite direction. And the opposite direction, you have the advantage that you're going to a group where you have Fourier coefficients. And you can compute explicitly Fourier coefficients, right? But now, if you're going between B and B prime, you don't have Fourier coefficients on either side. So you can't make this kind of computation. You need some new tool, and the new tool is the Rallis inner product formula. So this is something that tells you what the theta lift what the Peterson inner product of the theta lift of your form is in terms of the original form. So in this case, it will say that if I start with a form FB and make a theta lift with respect to, so actually this is going to be a pair FB comma chi. So I should just say FB comma chi. So the first thing I should have said is the level of representations, this will send pi chi to pi dual chi inverse, okay? Or 0. There are two possibilities. So it will go to 0 if something bad happens to the epsilon factors, or if the L value vanishes. If everything works out right, then it will go exactly to pi dual comma chi inverse. And then you can ask, what is the lift of such a form? What is the Peterson inner product of such a form? And it turns out that it equals exactly this L value times the inner product of the original form. That's the structure of the formula. Of course, when you compute it, it's a horrendous mess, and there's a lot of work that needs to be done. But anyway, so that's the key ingredient. And then the last thing that one needs to show is that if B is, let me say it this way, if the set of places, or let me say, if B is more ramified, or at least as ramified, as B prime at infinity, then this lift is algebraic. Okay. So in Harris's original paper, he made B more ramified than B prime by increasing its ramification at exactly one place. Okay. But the only observation you need is to kind of remove this condition that it has to be discrete series at one finite place, is to note that this holds more in somewhat more generality. But as long as B is at least as ramified as B prime, then this lift is algebraic. And well, there are natural rational structures and integral algebraic structures on both sides, right? On B and B prime. And so all I'm saying is that your form f sub B cross chi, it'll lift to something like f sub B prime cross chi inverse, right? Maybe with some scalar in front. And all I'm saying is that scalar is algebraic. Okay. That's all I'm saying. Yeah. Sorry, the inner product over here. The inner product is happening on this group on the right hand side. So this inner product is on GU E B prime. Make sense? Yeah, and proving this is algebraic involves a seesaw pair. Basically, again, you use the same idea. You restrict to CM fields. So you have some kind of. So let me just say a word about that. So you're lifting from UB to UB prime, and you can write B prime, remember, as K plus Kj prime, say. So think of this as V1 plus V2. Each of I'm used to writing K. I should write E. Okay. Right now, each of these is a unitary space over E. So what you get is a seesaw pair of the following kind. Okay. Now the UV1 and UV2 are just U1, and these are just U1s. Okay. And the lift that you have in this direction is just the theta lift of a character. Now we understand the theta lift of a character of a Hecke character of a CM field to GL2, right? Those are the usual theta functions that you can kind of write out. But now you're lifting to a non-split quaternion algebra. And it turns out the arithmeticity of this is quite subtle to understand. So Harris needs to understand that, and to understand, so right here, right, to understand this lift from U1 to UB, this is again subtle. Harris again uses the Rallis inner product formula. So I just wanted to briefly mention all the ingredients in the proof. The key new idea is that you can't compute with Fourier expansions, but instead you have the Rallis inner product formula, and that's the key point. So now I want to move to the setting of quaternionic unitary groups, where I'll explain things in somewhat more detail. So everything I'm going to say henceforth is joint work with Ichino. And in fact, we started off thinking about a completely different problem. And this problem is related to something that came up in Henri's first talk. So I'm going to start by explaining that. And that will kind of link up these lectures to some extent. So if you remember from the last class, so last time, we talked about a formula relating period integrals to L values. This formula is in fact due to Walsh-Burchet. And there are also contributions by Tunnel and Saito in understanding exactly when you should expect such a formula. So let me tell you what the general setting is. So the general setting is I have a field F, a number field F. I have a representation pi on GL2 of AF. Let's say F is totally real for our case, just to fix ideas. I have an I have an extension, a quadratic extension, which let's say is CM, E over F, such that, and a Hecke character of E. Okay. And I assume, I make this assumption that I made in the previous, or at least this assumption came up when we talked about unitary groups, namely that if I take the central character of pi and the central character of chi, and I multiply them, I get 1. Okay? So let's put ourselves in a situation where the products of the two central characters is 1. Now, you can do the following. Let's say that B is a quaternion algebra, such that pi transfers over F to some pi B on B cross. And you can pick some form F sub B in pi B, and you can ask yourself the following question. Suppose suppose for example that, and suppose that E embeds in B also, then I can take the form F sub B, which is a form which lives on B cross A. I can restrict this to E cross A and integrate it against chi. And the question is, when is this not 0, and what is it related to? Okay. So the theorem of, which is due to Tunnel, Saito, and Walsh-Burchet, Tunnel, Saito, Walsh-Burchet, is that given pi and chi with this assumption, right, that the product with central characters is 1, and further such that the epsilon factor at 1/2 of pi cross chi, which I'll just write epsilon half pi chi, is plus 1. Okay. So this is just the sign of LSF chi. So once again, LSF chi is the Rankin-Selberg L function associated with F and the theta function attached to chi, which you can also think of as the base change of F to E twisted by chi. Because of the assumption that the product of the two central characters is trivial, the corresponding motive is self-dual. So in fact, the sign is plus or minus 1. Okay? And so let's say that the sign is plus 1. If the sign is plus 1, then you expect that the central value is generally non-zero. Okay? And so you might want a formula for what L half is in terms of a period. Now the theorem exactly tells you what happens. It says that given such a pi and chi, there exists, and of course I should say E, right, because chi is on E, there exists a unique quaternion algebra B such that pi transfers to pi B on B cross, and there exists some FB in pi B with this integral squared being exactly related to the L value L half pi chi. Okay, up to some factors, and I'm going to kind of ignore these factors. There are some normalization factors that I've ignored.
Sorry, the quaternion algebra is the one which verifies exactly which the epsilon b is 1.
So let me say, I'll say a word about that since you asked. Okay, right. So the quaternion algebra is determined by local epsilon factors, and I can tell you exactly what the condition is on the epsilon factors. So the condition is exactly that. So the condition, maybe I'll put that up there. So epsilon sub v of b should equal following psi pi v of minus 1 times epsilon sub v of 1/2 pi chi. That's the condition. So you take the local epsilon factor, the Rankin-Selberg L function, you multiply it by the central character of minus 1 for that place, and that should equal epsilon v of b. That's the exact condition. Yes. What is it?
Is it after the square of the?
Okay, so you can, the original formula has the absolute value squared, but you can make it a square by being more careful. The reason you can do this is because this is self-dual. I mean, if there's some self-duality that's in here. So if you're careful, then you can make it a square. Okay. Yeah. All right. So that's the first formula. The second formula is the triple product formula, and the triple products came up in Henri's talk, in Richard's talk. So the second famous formula is the triple product, right? And so this says the following: suppose I take three guys, pi 1, pi 2, and pi 3, on GL2AF, and now assume that the product of the three central characters is trivial. Okay. Now you can look at the triple product L function, LS pi 1 tensor pi 2 tensor pi 3. This has an epsilon factor. So suppose further that the epsilon factor 1/2 of pi 1 tensor pi 2 tensor pi 3 is plus 1. Okay. Again, this condition implies that it's self-dual, and so the sign of the functional equation is to be plus or minus 1. And suppose you're in a situation where it's plus 1. Then so the formula here is due to, so originally due to Harris-Kudla. I guess I should say there's work of Garrett that went into this, and then Harris-Kudla, and then this was refined by Watson, and there's work of Ichino and Ikeda. There are lots of people who worked on this kind of thing. But what it says is then there exists F1, F2, F3. Oh, sorry, I should say this first. Then there exists again a unique quaternion algebra B such that all the three representations, pi 1, pi 2, and pi 3, transfer to B. So to pi 1b, pi 2b, pi 3b, and forms, which I'll call, say, F1b, F2b, F3b, right, in these representations, such that you have an integral formula of this form. The product F1b times F2b times F3b squared is again equal to some explicit factors to the L value L1/2 of pi 1 tensor pi 2 tensor pi 3. Okay?
And this is not real value, or you send it to.
You can, yeah. Anytime you have one of these formulas, you can extend it to the squares if you're careful. Though people typically aren't careful, so it's okay. So here are two beautiful formulae, right? And the question is, are these related in some way? Okay. Now, the L function here is a Rankin-Selberg L function. It's a degree 4 L function. The L function on this page is a degree 8 L function. Okay. So, and generally this will not factor. So if you put yourself in a situation where the degree 8 L function factors as a product of two degree 4 L functions, then you might expect a relation between these two formulae. Okay. So what is the situation where exactly that happens? So are these two formulae related? Okay. And here's a situation in which they are related. So let's take pi 1 to be any pi whatsoever. Let's take E over F to be a quadratic extension, say Cm. Okay. And let's take two characters, which I'll call eta 1 and eta 2. These are Hecke characters of E. Okay, and now the condition, and now I want to take pi 2 to be pi eta 1 and pi 3 to be pi eta 2. Okay, so these are the theta lifts of eta 1 and eta 2, these two characters, the eta 1 and eta 2. And the condition of the central characters is exactly going to be that psi pi times psi eta 1 times psi eta 2 equals 1. Okay, that's the condition you would get because, right. So let's say you put yourself in that condition, in that case. Now, what happens to the L function? So the L function that you have is L half of pi tensor pi eta 1 tensor pi eta 2. Okay? Yes. Oh, up. Okay. All right. And precisely because eta 1 and eta 2 are both Hecke characters from the same field, this L function factors. Okay? It's very easy to see this. It factors, I shouldn't say L, let's look at the whole L function. This is going to be Ls of pi chi 1 times Ls of pi chi 2, where chi 1 and chi 2 are related to eta 1 and eta 2. And the relation is just that chi 1 is going to be something like the product, and chi 2 is going to be the product after you apply the non-trivial involution of E. So let's call rho, so E over F is this quadratic extension, and rho is, say, the non-trivial Galois involution there. Okay? All right. So let's stare at this formula. So here we have a formula that relates three different L values, or three different L functions. Let's look at it at 1/2. And let's also suppose we're in a situation where the signs are all plus 1. Okay? All right. So you have three L values. The signs are plus 1. So each of them is related to the square of a period, right? Okay. So I'm just going to move this up here. This is going to be the square of something like FB1, maybe F1. So let me not. I'm just going to say this is the square of something. This is the square of something. And this is the square of something, okay? All right, make this more precise in a bit. So you have a relation that says the square of something equals the square of something times the square of something, okay? So an obvious question, can you prove this without the squares, okay? Now, the interesting thing, remember, is that each of these guys occurs in a quaternion algebra, right? But you're going to get three distinct quaternion algebras in general in this way. There are three different quaternion algebras, okay? Now, there must be some relation between them, right? So if you look at the epsilon factors, right? So here, again, you can say exactly, I should have said what the quaternion algebra B here is in the triple product. You exactly need epsilon V of B to be epsilon V of 1/2 pi 1 tensor pi 2 tensor pi 3. Okay? So now you just compute, you stare at this and you see that the relation between, so let me write again here. So this is going to happen in some quaternion algebra B. This will happen on some quaternion algebra B1, and this one on some quaternion algebra B2. And the relation between the three is going to be that B equals the product of B1 and B2 in the Brauer group. That's the relation you use. So B okay. So in fact, any two of them will multiply to the third in the Brauer group. Okay. All right. So now we want the question we in fact wanted to address was, can we prove such a period relation directly without the squares, right? Okay, I want to explain how one can do that, and that will naturally tie up with the other problem. Okay, so the idea is the following. Let's pick. So remember that. So I'm going to go back here, right? Remember that eta 1 and eta 2 both started life on the same CM field, right? And chi 1 and chi 2 are Hecke characters in that CM field. Okay? And these formulae that involve the squares of the periods use an embedding of E in B1 and B2. So the very fact that such formulas exist imply that your field E embeds in both B1 and B2. Okay? Now, since BE embeds in both B1 and B2, E also embeds in B, because B is just the product of the two in the Brauer group, and that's you can check that. Okay. Now let's write B1 as E plus EJ1 and B2 as E plus EJ2. Okay, in the way that we've been doing. And let's say that, so J1 and J2 will be elements of trace 0. So trace of J1 equals trace of J2 equals 0. And so their squares will live in the base field. So I'm going to call that capital J1. This will live in F. And likewise capital J2, which is J2 squared, will also live in F. Okay? And you can think of B1 and B2 as right E spaces. So think of B1 comma B2 as right E spaces in the way that we just did, right? And in fact, they are unitary spaces. Right? That's right. They're unitary spaces. Okay. All right. So you get in this way, you get right. So B1 and they're both two-dimensional, right? So B1. Right there. So B1 and B2 are both two-dimensional right E spaces, and they're equipped with natural forms, which I'll call. These are the same forms that I defined before when I thought of them as unitary spaces. Okay, now let's do the following. Let's take the tensor product of B1 and B2 as E spaces. So that's the four-dimensional E vector space. Okay, all right. What I'm going to do is make this into a right B module. Now remember that because E embeds in both B1 and B2, this implies that E embeds in B as well. Because B is just the product of the two in the Brauer group. You can just check what the condition is. But let's construct B explicitly. Okay? So what's an explicit model for B? We already know, we've written down explicit models for B1 and B2. So it turns out B you can just write as E plus EJ now, where J squared is going to be J1, J2. Where J1 and J2 are J1 squared and J2 squared, respectively. Little J1 squared and little J2 squared. Okay. So I want to make an action of B on this space. I already know how E acts because these are E vector spaces. So basically I need to tell you how J acts, and I need to make that consistent. Okay? Alright, so I'll tell you how J acts on the basis vectors. So this is four-dimensional as an E space. And a basis for this is just one tensor 1, J1 tensor 1, J2 tensor, one tensor J2, and J1 tensor J2. Okay? All right. So I have to tell you how J acts on each of these. And there's an obvious guess that you would make. You make J act on one tensor 1 by sending it to J1 tensor J2, on J1 tensor 1 by sending it to J1 times 1 tensor J2, on this guy by capital J2 times J1 tensor 1, and this guy by J1 J2 times 1 tensor 1. Okay? And then if you check, this gives you an action. It can be done. Okay? So check this. This gives an action. Okay? So what's happened is this four-dimensional E space is now a two-dimensional right B vector space. Okay? So this guy is a two-dimensional right B space. Okay? We want more than that. We want a form, right? Okay. Now we have these two forms, bracket 1 and bracket 2. So I can just tensor these two forms. Now bracket 1 and bracket 2 were Hermitian forms to start with. So when I tensor it, I get something that is it's Hermitian. What I do is I make this. So that's a E Hermitian form. So let's pick some element alpha, which is an E of trace 0, and alpha is not 0. And let's multiply this form by alpha. And when you do that, then so this gives you a new form, which I'll call just bracket. So this is a form on B1 tensor B2. So this is just a Hermitian form, right? An E Hermitian form. Right? In fact, E skew Hermitian form. This is a skew Hermitian form on this space. Okay? So far, at this point, I'm only thinking about these guys as E spaces, right? And so I've got a four-dimensional E space, and I've made a skew Hermitian form on this space. But what I want is a B skew Hermitian form. Okay, and in fact, so I won't write this down explicitly, but I'll just say that one can find a B skew Hermitian form which I'll call on, let's give this guy a name, let's call this V, okay, on V, such that the if I take this form, this is going to be B valued, and then I take the projection onto the first coordinate, so PR onto E of this form. This in fact recovers the skew Hermitian form that I constructed over there. Okay. All right. So now what I've done is I've got a two-dimensional B space, okay, and I have a B skew Hermitian form. So this form, by the way, satisfies the following. It satisfies X alpha Y beta equals alpha I X Y beta. This is for alpha and beta in B cross, and it satisfies X Y equals minus YXI. Okay? So this is the skew Hermitian nature of it. All right. Okay. So so there's some interesting non-commutative algebra that goes into this, but now the idea is you look instead. So instead of looking earlier, we were looking at unitary groups, and now we are going to look at quaternionic unitary groups. So let's take the unitary group GUBV. Okay. Right. So V is a B space, a right B space. So I'm going to look at linear automorphisms of equipped with a B skew Hermitian form. So I'm going to look at linear automorphisms of V that preserve this B skew Hermitian form up to similitudes. Okay. And well, what is this? Well, it turns out you can check that if you look at there's a natural action of both B1 and B2 on B1 just by left multiplication, and it turns out this preserves the form. Okay, so this guy is basically B1, at least its connected component is just B1 cross cross B2 cross mod a diagonal F cross. On the other hand, what I can do is I can take W to be just the space B itself, equipped with the usual B Hermitian form. This is just xy equals xiy or xyi. And I can think of the unitary group GU BW. Okay? And this turns out to be just a copy of B cross. And now there's a theta lift from here, from GUBW to GUBV0. And so where it goes from is from B cross to B1 cross cross B2 cross or F cross. Okay. Now if you have such a lift, you can imagine what this lift must be, right? This lift is either going to be 0 or it will send a representation to its Jacquet-Lagrange transfers. Okay. So the first theorem that one needs to prove is that the theorem in this case, we've assumed that pi transfers to everything. So pi b, the theta lift of pi b is basically going to be pi. All right, okay. So I won't say anything much about the proof of this, but the point is that, again, you can't use Q expansions. You have to use the Ralston product formula to even prove something like this. But the interesting question that you can ask is, if I start with a form, okay, so firstly, if I start with the form FB, this is going to lift to some multiple of FB1 cross FB2. Okay? And there is going to be a dual pair So that's a dual reductive pair, where it turns out that there's a seesaw pair of this form. Okay. So your form F is going to lift to a product of two forms over there. You can restrict this to a product of two copies of E cross and integrate against two different Hecke characters. When you lift it on the other side, you get a triple integral, right? So the seesaw duality, which I talked about last time, just implies the equality of the periods that you want. Okay. So remember, we wanted to show this equality of these three different periods. The product of two of them should be the third. Just a simple application of seesaw duality. You don't need the various formulae for this. Okay. But now the really interesting part just starts, because you want to understand, if you start with the form FB and lift it to the other group, what happens with the arithmetic properties of this lift. Okay? So F sub B is going to lift to some alpha B1 B2 of F sub B1 cross F sub B2. Okay? I'm going to call that alpha B1 B2 because B is determined by B1 and B2. What can we say about this alpha B1 B2? Now again, we have to use the Rallis inner product formula. So the Rallis inner product formula will tell us that the inner product of the lifted form equals the inner product of the original form times an L value. And the nice thing about the setup is that the L value is no longer a central value, it's the adjoint L value. It's exactly what you want it to be. So Rallis will tell you that alpha B1 B2 squared times FB1 FB1 times FB2 FB2 equals the original guy times the adjoint L value. Okay? Now this thing is ripe to throw in our conjecture from the first and two lectures. Sorry, adjoint of pi. I call that pi. Pi is the single pi. Okay. So now let's throw in our conjecture from the previous lectures. Right. We have a very precise conjecture for what these Peterson inner products should be. Right. So that conjecture says that this guy should be the adjoint L value divided by the product of the CVs where V is in sigma B1. This guy should be the adjoint L value divided by the product of the CVs for V in sigma B2. Well, this guy should be the adjoint L value divided by the product of the CVs for V in sigma B, and then you have an additional adjoint L value. And happily, the adjoint L values all cancel, right? So what do you get? You get alpha B1 B2 squared should be the product of the CVs where V is in sigma B1 times the product of the CVs where V is in sigma B2 divided by the product of the CVs where V is in sigma B. But let's not forget, B is the product of B1 and B2 in the Brauer group. So if you have a place that is only in B1 or only in B2, you get cancellation. If you have a place that is in both B1 and B2, then it's no longer in the denominator and you get a square in the numerator. So this is exactly the product of the CV squareds where V is in sigma B1 intersects sigma B2. Okay, and so alpha B1 B2, well, up to plus minus 1 I guess, and everything is should just be the product of the CVs where V is in sigma B1 intersects sigma B2. This page I wrote like this. That's unfortunate. Okay, but this now tells us, but remember now what we expect for the CVs, right? You expect that if V is an infinite place, then CV is transcendental, but if V is a finite place, you expect CV to be an algebraic integer, right? So now this leads naturally to the following conjecture. If sigma B1 infinity intersects sigma B2 infinity is empty, then alpha B1 B2 is algebraic and is in fact a P integer. Okay. Right? Because you should only pick up algebraic things on the right side, they should all be integers. If further sigma B1 finite, further sigma B1 intersects sigma B2 is infinite. So if they have no finite places of ramification in common either, then this should be the empty product. And so then alpha B1 B2 should be a P unit. Okay. So this is a very natural conjecture that is implied by what I said before, along with this expectation about things being algebraic and so on. Okay? So I'll call this conjecture B, and suppose the previous conjecture is conjecture A. So in fact, we can show quickly that conjecture B in fact implies conjecture A. Okay? And I'll say a couple of words about this. So let's say we knew conjecture B, and you want to prove conjecture A. Conjecture A says there should exist CVs, right? So you have to produce the CVs somehow. Okay? All right. So let's do the following. Let's note that, well, what does this relation tell you? So conjecture B, so let's define the following. So we need to define the C sub V's for all V in sigma pi, where sigma pi is a set of places where pi is discrete series, right? So let's do the following. So let S be any subset of sigma pi with even cardinality. In that case, let's define C sub S to be the adjoint L value divided by the inner product of F. I'll call this, right, this is Fs, where by Fs I mean a form, or a normalized form on a quaternion algebra which is ramified exactly at S and that pi transfers to. Okay? This makes sense because S is an even set of places, so I can find a quaternion algebra, exactly one quaternion algebra that is ramified, that's even set of places. So that defines C sub S. Now, if you go back to this relation on the previous page, what that tells you, along with this conjecture B, that will imply that C sub S defined in this way satisfies the following. If I take a disjoint union S union T, then C sub S union T is the same thing as C sub S times C sub T. Okay? That's what conjecture B will tell you. All right. Now it's clear how you should define C sub V. So to define C sub V, you pick two other places, R and S, two other places in sigma pi, and define C sub V by the formula C sub V squared is CVR, CVS divided by CRS. Okay. Right. Okay, now you want to check this is independent of choices. So let's say you replace S by T, then you want to show that CVR, CVT by CRT equals CVR, CVS by CRS. Right? Now the CVRs cancel, and what you want is CVT times CRS equals CVS times CRT, but this is exactly this relation that we have over there. And now so this defines C sub V, and then it's very easy to see that they satisfy the right multiplication properties. Okay? So now for a general, it's easy to see that C sub S is just the product of the C sub V's for V and S. So everything follows from here. Okay? So you want to go back now and prove conjecture B. Right. Now, what we can check so far is we can check the algebraicity. Okay? And certainly that gives a different proof of this theorem of Michael Harris. It doesn't use this condition about being discrete series in some finite place doesn't occur anywhere. You don't care about that at all. And I have some ideas on how to prove it's a p integer and it's a p unit, but this will require a different lecture series, and certainly not here. Now, the reason this is better than the approach using unitary groups is in the approach using unitary groups, you have lifts on both sides, and you have some things that should be p integers, and then you need to prove various cancellation statements if you want to do that. But it's very, very hard to prove cancellation statements. The best thing to do is just set yourself up in a situation where something should be a p unit, and then try to prove it's a p unit. And this is exactly what you can do in this setting, using these three different quaternion algebras. So it's a nicer setting to work in. I guess out of time, and I'll stop here.